Okay, here it is, the last of the video lectures. Physics 105A video lecture 17. And it's going to be a short one. I just want to make some announcements and a little heads up about the final exam. So, first of all, any homework you want to turn in, just get it to me by Friday of this week, the 8th of May, and then we'll draw a line under it. Anything else we want to do, we'll just pick it up next semester. Okay, so I'm not worried about that at all. The exam, Monday, May 11th at 8:45. So 8:45 to 10:45. I'll send it out a few minutes early, or 5, 10, 15 minutes early, doesn't matter. But we do want to maintain this deadline here. So at 10:45, I want them to be in. So make sure you have your technique for taking good pictures and scans and what have you dialed in. And say we have 5 problems on the final exam, then you've made a good shot at all 5 of them, taking your pictures, get them into me at 10:45. Yeah. So that is that, it worked fine on the midterm, so that was really a dry run for this, and I'm confident that this will all work pretty well. So what do we have for this exam? It's really a rerun of the first 2 midterm exams. Okay, so study the first 2 midterms and all of the material that surrounds those midterms, and then you'll actually be fine. So I'll give a little list reminder of how that works. We start out with some vectors and kinematics. I'll just come up with another interesting problem of that type, okay? And then we were into one-dimensional dynamics, so one-dimensional Newton's law. dv dt f of x v t. That whole generality there where we did integration and solved that type of stereotypical problem. After that, we're still in one dimension: force, potential energy, and potential energy with a local minimum, so U of x with a local min. Taylor expansion, local minimum, small oscillations. Okay. And when we're looking at this, set of circumstances, then this culminates in omega squared is u double prime x naught over m, that kind of thing. So small oscillations if you have a second derivative. So good, there's that type of problem. And then there's the small oscillations formalism proper. And there was the problem that we didn't do on the last exam that I think I'll put one on the final exam, namely when we had the undamped oscillations and the formalism that went with that. Right, we went into the complex plane. So go dig that up out of your notes and understand and practice those, right? And then we did an integration, and we finally ended up with x is the imaginary part of c over omega naught. So we could have a problem of this type. Well, I've got more board available. Let's send this up here. Yeah, so what else? Then we have our central force formalism. Now, since that exam, we've actually gone much deeper into the central force. We solved the entire Kepler problem. Okay, we've done some pretty sophisticated stuff with the scattering. We've even moved on into multi-particle, many particle systems. But that material doesn't lend itself as well to an exam, okay? So we'll discuss that in person next semester when we pick up where we left off here. So if I talk about central force, it's really the type of problem we were prepared for last time as well. So again, with the central force, there's the whole progression. Okay, from your, in fact, one body force problem. This can be a reduction to the two body problem, as it was with the Kepler problem, and that's your reduced mass, otherwise it's just a mass. Yeah, so this whole thing and onward. So in particular, then you want to be able to discuss an effective potential and analyze it. There's the basic stereotypical Kepler problem, effective potential. And with the effective potential, very clearly here, energy is less than zero, bounded orbits, energy is greater than zero, unbounded orbits. So you'll notice, I may not have brought this up as clearly, when we did the scattering, okay, when we did the scattering problem, the Rutherford problem, of course it was repulsive, so we were the positive energy in the regime of unbounded orbits, but we could have done scattering with an attractive potential, okay? Rutherford was repulsive. If we had done scattering with an attractive force, as long as our potential is, as long as our effective potential energy is greater than zero, okay, as long as the energy is greater than zero, then you're in the unbounded regime. A particle comes out from infinity, reaches a minimum of closest point, and goes back out to infinity. Okay. Then you've got the circular orbits, and in fact, since the last exam, we did go into circular orbits in more depth and systematically. So circular orbits, the apsidal angle formalism, where you have omega sub phi T sub r over 2, and under appropriate circumstances, that turns into this wonderful formula, 3 plus r u double prime over u prime of r naught. You can't always use this formula. You have to actually be in a central force problem proper. The central force table doesn't actually allow this formulation here. Okay, so that's the type of thing as far as we want to get. I should add one more thing that would be fair game. Gradient, divergence, curl of these kinds of R, F of R. Of those types of problems here. Of those types of scenarios, you get the vector, you've got its magnitude, you've got a function of the magnitude. And we did some of that on the homework, and in class I showed a bunch of that as well. So you could say those are skills that go with the central force problem, and they lead into the many body stuff that we're going to do next semester. But we did Kepler problem, we did scattering. We've already done some pretty sophisticated stuff, and we've done point systems. And you'll realize when we did this how they all built on each other, these topics here. And built on this, but they're not as good for a 2-hour exam. Okay, so we'll talk about those more later, namely next semester. So yeah, I'm gonna cut it pretty short today. I'm gonna wish everybody luck on this, good luck on this exam and all of your other exams as well. In a week or so, a little week and a half, we'll be done. As far as all the material we covered, you really have a good compendium of mechanics now. So you've got all summer. If you weren't satisfied with how well you mastered it, you've got all summer to go over it. The order that I've presented it in is very systematic, and it just leads into what we're going to continue doing. Next semester we have Lagrangian mechanics, we have some potential theory, we have rigid body motion, and actually towards the end of the semester, fluid mechanics, if we should get that far. So more great stuff than you can even imagine. Okay, good. See you guys next time.